Welcome to Mathmania Academy. In this video, we are going to discuss the Part C questions of linear algebra which were asked in December 2015. The first question is given as V is given to be a vector space of polynomials over R of degree less than or equals n. So whatever may be the element that we take from the vector space V, which is in the form of P of x, which is given as a0 plus a1x plus etc. till an x power n. Okay, and we define a linear transformation from V to V in a fashion that Tp of x is given to be an plus an minus 1 of x plus etc. till a0 x to the power n. So basically what does it do? You are able to I hope you are able to understand the definition of a linear transformation which is given in the problem. Okay, for this we shall consider a basis. Okay, so the basis shall be treated as 1x x squared etc till x to the power n. So the number of elements in the basis is n plus 1. So if you try to identify the matrix associated with this transformation with respect to this basis, that is going to be of order n plus 1 by n plus 1. Okay, we shall identify the matrix and then try to do the rest of the calculation of the problem with the help of the matrix. First of all, what is t of 1? So it means it has only a naught value which is 1, that will be associated with this x power n. So it is x power n. And what is t of x? It is a1. So here a1 will be, by the definition, it will be associated with x power n minus 1. So that a1 will be the coefficient of x power n minus 1. So then t of x squared would be x to the power n minus 2. In this fashion, t of x power n would be what? It is simply 1. Now if you put this in a matrix form with respect to the standard basis that we have considered, it is 0 0 etc. Goes till 1, excuse me, 0 0 etc. till 1 0. So and it goes this way, and we would have 0 1 etc. 0 0 and then 1 0 etc. till 0 0. Okay, this is the matrix which is associated with the linear transformation. Now if you closely look at the matrix T, you are able to identify that after some interchanging of columns or rows, okay, after a certain stage we will get an identity matrix. So we are not doing any other alteration, we are just interchanging either rows or columns to get an identity matrix. Why am I saying this? Just by interchanging the rows or columns, the rank is not affected. So by doing some alteration, you are going to get an identity matrix, which means the rank of T is same as that of the rank of identity matrix, which is n plus 1. Okay, so the rank of T is n plus 1. Now by rank nullity theorem, rank of T plus nullity of T equals what? Dimension of V, which is nothing but n plus 1. And we have found that the rank of T is also n plus 1. So this together gives us that nullity of T is 0. If the nullity of T is 0, which means what? This tells us dimension of kernel of T is 0. Okay, which means the kernel consisting of only the excuse me, 0 element. Kernel consists of only the 0 element. Therefore T is 1 1. Okay, what is range of T? Rank of T. Rank of T is the dimension of range of T. Okay, and we know that range of T is a subspace of the codomain, which is V here. Okay, so basically range of T is a subspace of V and they both have same rank here. Hence this mapping T is onto. Actually this is same, and rank of T is same as that of the dimension of V, which tells us that range of T is entire V. Therefore T is onto. So when we proved both when we prove t is both 1 1 and on 2, the mapping becomes invertible as well. Okay, basically, if the linear transformation is invertible, then the matrix associated with the linear transformation is also invertible. Okay, so in order to prove the invertibility, we'll have to examine the determinant of the matrix. Okay, let us do it. If you can directly calculate the determinant of this matrix, this is quite fine. If not, just try by an induction hypothesis. Like, first of all, let me consider only the constant polynomials are present inside V. In that case, my T would be simply a matrix with 1. So the determinant is 1 here. If T is like, if V is my polynomials of degree 1, then this is going to be my T. Therefore determinant of T is minus 1. So go for the higher dimensions ones, 3 by 4, 3 by 3 and 4 by 4. In all these cases, you are going to get determinant is either 1 or minus 1. In no case determinant is 0. So if it in no case the determinant is 0, of course T is invertible, right? Okay. Moving to the next question. Here V is given to be a finite dimensional vector space, and T is a linear transformation which is defined from V to V, such that rank of T square is given to be rank of T. Okay, this is the basic idea that we have. Okay, now basically if you have two linear transformations, then you have the result that rank of AB is same as that of rank of A minus dimension of kernel of A intersection range of B. You have this property. If you take A and B both are equal to T, then what you are going to get is rank of T square is rank of T minus dimension of kernel of A kernel of T intersection range of T. Okay, so since rank of T square and rank of T are equal, what we get is dimension of be it minus or without minus, dimension of kernel of T intersection range of T is 0. If the dimension of some space is equal to 0, which means that space is a 0 space. Okay, option 3 is a right one. Okay, basically this is one way of proving kernel of T intersection range of T is set 0. The other way is we know that V is given to be a finite dimensional vector space and T is an operator which is defined from V to V. So we can basically split this V as kernel of T direct sum with range of T. If it is possible, then it means what? Kernel of T intersection range of T is set 0. Okay, this is possible only when V is a finite dimensional vector space and T is defined from V to V. Only then this is possible. Okay, so in both the ways we can prove option 3 is true, right? Next we will check the option 1, for which let me choose an element from kernel of T, which means Tx is 0. Okay, so basically kernel of T and kernel of T square, let me just write down the definition. It is the collection of elements in V such that Tx is 0. Okay, I don't know whether you people can see here because of the logo. Okay, hope you know the definition, right? So first of all, here the main thing that I need is kernel of T square. Okay, which will be used. It is the elements in V such that T square x is 0. If it is T, you can replace very well. Okay, we have Tx equals 0 whenever x is a member of kernel of T. When you apply T to it, T of Tx equals T of 0. Since T is a linear operator, it is 0. Therefore, T square x is 0. X is a member of kernel of T square. So this tells us that kernel of t is a subset of kernel of t square. And now let us take x as a member of kernel of t square, then t square x is 0. So this may be written as t of tx is 0. Now using the definition of kernel of t, okay, what does it imply? This tx is a member of kernel of t. But basically, where does this tx belong? Set of all y which takes this form is a member of range of t, right? So basically this tx is a member of range of t, and here this tx is a member of kernel of t. So what we have is this tx is a member of kernel of t intersection range of t. Since we proved the option 3 is right, this is possible, like this is the set, okay. Therefore tx has to be equal to 0. If tx is 0, this means what? X is a member of kernel of t. Therefore kernel of t square is contained in kernel of t. Combining these two things, what we get is kernel of t is same as that of kernel of t square. So that is option 1, right? And the next one is, we'll go to option 2. There we'll have to prove range of t square and range of t are equal. Either we'll have to prove or disprove this. Basically what we know is range of t square is a subset of range of t. How do we conclude this? Okay, basically range of t square means what? It is the elements of the form t square x, right? So this may also be written as t of x. So this one, let me write it as ty. Okay, so I have started with z. Okay, so this may be written as t square of x, and this may be written as t of x, and this tx I am writing it as y. If you see here, this x I have taken from v, this y is also a member of v. Okay, so this z may be written with the help of t square. When you operate this t square to x, you are getting z, or if you operate the operator t to y, you are getting z. So basically you have started with an element in range of t square and finally proved that is an element of range of t. This is happening to be true. Good, that's fine. Okay, now if you see here, what do you get? Okay, I think we don't need this one. It is given that rank of t square is same as that of rank of t. That is, dimension of range of t square is same as that of dimension of range of t. And since range of t square is a subspace of range of t, we conclude that range of t square is same as that of range of t. So option 2 is also right. Just make use of the option 1 and 2. In 3, you would get option 4 is also a right one. Okay. Now we move to the next question. Here, A and B are two matrices, two n by n matrices which are considered over C, which means the entries of the matrix A and B are complex numbers, right? Okay. As of now, let me state a result that if A is a matrix of order m by n, and B is a matrix of order n by m, then the product AB and BA is well defined. This is a matrix of order, let me call it as Cij. Okay, this will be a matrix of order m by m, and this BA will be a matrix of order n by n. Hope you know how this Cij and Dij are defined, right? So for this matrix, this is a square matrix and this is a square matrix. Basically A and B are not square matrices. in the case that I have considered. But this AB and BA are square matrices, hence the characteristic polynomial of these things can be found. So associated characteristic polynomials, let me write in this form. The relation between these two characteristic polynomials are given by okay, basically this will have the degree m and this will have the degree n. So you just multiply x to the power n here and x to the power m here. Now both will have the degree m plus n. Okay, this is the relationship between the characteristic polynomials of AB and BA. Right? Hope you have got the idea. Now, coming to the problem that we have here, both matrices are given to be of order n by n. So in this case, what happens? Characteristic polynomial of AB of x, and this is x power n, and again here we'll have x power n, characteristic polynomial of BA of x. So this x power n gets cancelled on both sides. So what we have is CAB of x is same as that of CBA of x. That is, the characteristic polynomials of both the matrices are same. If the characteristic polynomials are same, then of course the eigenvalues are same. Therefore, option 1 is a true one. Okay. Now, let us check. If A, B and BA have the same set of eigenvalues, yes, of course. No matter what A and B we choose, but we are getting the same eigenvalues for the product AB and BA. Okay. Here in option 2 they have said that if they have the same set of eigenvalues, then the matrices should commute. That is what they are saying in option 2. That need not be true. For which, let me choose some matrices. A, I am choosing it to be 0, 1, 0, 0, and B, I am choosing it to be 1, 0, 0, 0. If you make the product AB, what you are going to get is a 0 matrix. You can make a product and check. And when you find BA, you would get 0, 1, 0, 0. Of course, the the characteristic polynomial and the eigenvalues, they are same. Yes, of course, they are same. But AB is not same as that of B. Okay, so option 2 is false. Next, they are talking about the similar matrices. When do we call two matrices are similar? If P and Q are similar, or if you have to say these two are similar, okay, actually not if P and Q are similar. If P and Q are said to be similar, if there exists an invertible matrix R such that A may be written as not A, P may be written as RQ R inverse. Okay, here if you look at the definition, there exists an invertible matrix. So what we are trying to say here is there must exist at least one invertible matrix such that this expression can be written or this expression is valid. Okay, we don't need to look for all the invertible matrices, and if this condition is satisfied by all the invertible matrices, no matter what matrix we are choosing, it has to be an invertible matrix. There must exist at least one matrix such that this is holding true. Okay, so with this idea coming here, AB, okay, this may be written as AB A inverse because A is invertible. So multiplying A inverse, which is basically what, an identity matrix, right? So I may write this way. So this is AB A inverse. So here AB and we have A, then BA A inverse. If you use the property of associativity, yes, you have this. We are able to identify an invertible matrix which is nothing but A, such that this is true. Hence, AB and BA are similar. Okay, from the example that we considered, the A and B, it is very trivial that AB has rank 0 and BA has rank 1. Therefore, the rank need not be equal. Option 4 is false. Moving to the next question, it is given that A is a m by n matrix. Okay, m by n real matrix. That's it. Nothing else. And B is a vector in Rm with B not equal to 0. Okay. In the first option, they are asking whether the set of all real solutions of the system Ax equals B is a vector space or not. Whenever we are asked to examine some set as a vector space or not, we will see whether a vector addition is well defined, scalar multiplication is well defined, and the properties that connects the vector addition and scalar multiplication are holding true or not. These things we will see. But when we define vector addition, we will check whether the set V under that vector addition is an abelian group or not. There, the main property that we in most of the cases we take it for granted is the existence of zero element. Okay, we don't check it usually, mostly. Okay, I'm not saying everyone does that, but most of us, including me, okay, most of us, we just ignore the property that it will be there always. Okay. Okay, suppose, let me consider the case if z, okay, first of all, let me define s to be the collection in ax, so it is n. Okay, right? So x in Rn such that ax equals b. Okay, so this is what I am considering. It is the collection in Rn such that ax equals b holds true. If 0 belong to s, then what happens? Then my ax, which is nothing but a0, has to be equal to b, which means what? My b has to be equal to 0, but it is clearly said that my b cannot be equal to 0. I can choose any element in Rm which is not equal to the 0 vector. But if it has to be a vector space, then 0 element must be a member of it. If 0 element is that, then I am getting my b to be equal to 0. That cannot be possible. Hence, this cannot be a vector space. Okay, just by looking at the statement that it is a vector space, uh, you may go and start working out the abelian group properties and the scalar multiplication and all those stuff. But here the basic thing, whether 0 element is present in it or not, that fails. Okay, now coming to the second option, it is given that uh, u and v are solutions of the system. If u and v are solutions of the system, then au equals b as well as av equals b. Then we have something lambda u plus 1 minus lambda v. Okay, we have to check whether that combination is a solution of the system or not. Okay, let us examine a times of lambda u plus 1 minus lambda v. So we may split this as a times of lambda v plus a times of 1 minus lambda v. Since this lambda and 1 minus lambda are scalars, we just take it outside. A u plus 1 minus lambda a v. Fine. So what is a u, which is b, and what is a v, that is also b. So what we have is lambda b plus b minus lambda b, which is simply b. Yeah, here no matter what lambda we chose, this is turning to be a solution. So whatever may be the value of lambda that you choose, your lambda u plus 1 minus lambda v is a solution of ax equals b whenever u and v are solutions of the system, right? Actually, in the option 3 there is a typographical which I missed. Here in the option we have this only when. Okay, if this only when is not given, we don't have to care about the value of lambda. We can make a tick mark in option 3. But this, because of this only when, this option is turning a false statement. Why? because they are saying that this combination lambda u plus 1 minus lambda v will be a solution of the system ax equals b whenever, okay, whenever lambda value lie between 0 and 1. This is what they have said, okay, but that is not the case always. Here we have seen that no matter what lambda we choose, but we are getting that as a solution of the system. We have proved it in part 2, okay. Because of that, only when this option is turning as false statement, right? And in option 4 it is given that if rank of A is n, then it will have at most one solution. Okay, let us check it. If rank of A equals n, what is basically rank of A? Which is minimum of smaller than or equals minimum of m comma n. Okay, so of course this clearly tells us that m is less than sorry m is more than or equals n. Okay, when will a system have solution? That is when the rank of AB is same as that of rank of A. Okay, it is given that rank of A is n, which means it will have n linearly independent columns. It has n columns and all the columns are linearly independent. No matter what B you choose, rank of AB remains n and rank of A is also n. So the condition is satisfied, therefore the system will have a unique solution if the solution exists. Okay, if the solution exists, it will have one solution. If the solution does not exist, no worries. Okay, option 4 is a true one. Here exactly it will have a unique solution, but according to the statement at most one solution, what they are trying to say is that if we have a solution, we'll have unique solution. If it does not have a solution, no solution. That's it. Okay, option 4 is also a true statement. Moving to the next question. Here again we are given a n by n matrix over C such that every non-zero vector of Cn is an eigenvector of A. Okay. Here we are considering the space Cn over C. Right? The dimension of the space is n. Okay. So if you choose any n linearly independent vectors, that is enough to generate a basis, because n linearly independent eigenvectors in a space will span the space. Okay, so for lambda in C, let v1 v2 etc till vn be eigenvectors. Then what happens? Then A Vj equals lambda Vj for j running from 1 to n. Right? So this may be written as A Vj minus lambda Vj equals 0. This is nothing but A minus lambda I times of Vj equals 0 for j running from 1 to n. The same story is there. Now, the set v1, v2, etc. vn becomes a basis to the Cn of C since they are eigenvectors. Okay. So, any element can be written as a linear combination of the basis elements. Hence, okay, using that fact, a minus lambda I times of, I just multiply some alpha j to it. So, this is there. So, a minus lambda I alpha j vj, where this alpha j for some alpha j in C. This is happening. Okay, from which what can I say? J running from 1 to n, a minus lambda I alpha j vj is 0. This is nothing but a minus lambda I multiplied with summation j runs from 1 to n alpha j vj is 0. Therefore a minus lambda I v equals 0 for all v in this Cn over C. This is what we have. So this A minus lambda I, when you make a matrix multiplication with any vector in Cn over C, we are getting it to be 0. This means what? This A minus lambda I has to be a 0 matrix. Therefore, A has to be equal to lambda I. So what you get is A is lambda I. That is option 3. Right? We are done. Okay. Basically, A is lambda I, which means A is a diagonal matrix. If it is a diagonal matrix, then the eigenvalues of this matrix are lambda repeated n times. So all eigenvalues of A are equal. The second option states that all eigenvalues are distinct. That cannot be possible. Okay. Since A is a diagonal matrix, what? This matrix A is diagonalizable. If the matrix is diagonalizable, then the minimal polynomial of that matrix will have distinct linear factors. Okay. If here the eigenvalue is only one, that is lambda, so it will have only x minus lambda. But the characteristic polynomial is x minus lambda to the power n. So the characteristic polynomial and the minimal polynomial are different. They are not equal. So option 4 is false. Only option 1 and 3 are right. Moving to the last question of this video, we have two matrices A and B. With these two matrices, we are asked to check four options. A and B are similar. Okay, that we will check. A is diagonalizable over the field of rational numbers. If it has to be diagonalizable, then what should we prove? The minimal polynomial consists of only the linear factors, right? That we'll have to check. Okay. B is the Jordan canonical form. Okay, fine. So basically, we'll have to play with the matrix A, right? And in the fourth option, the minimal and the characteristic polynomial are same. This is given. Okay, fine. First of all, let us write down the characteristic polynomial of the matrix A. Since A is a upper triangular matrix, writing the characteristic polynomial is quite easy one. Okay. Now we'll have to check the minimal polynomial. With the characteristic polynomial, what can we write? Minimal polynomial has two options. One is x minus 2 multiplied with x minus 3, or x minus 2 whole square multiplied with x minus 3. If it takes the first option, if the first option is true, then A is diagonalizable. If the first option is not true, then A is not diagonalizable. Okay. The question will be resolved if we find the minimal polynomial. Okay. In order to find the minimal polynomial, what should we do? Okay. So we will check for the geometric multiplicity of the matrix. Geometric multiplicity when lambda equals 2. So geometric multiplicity when lambda equals 2. This is defined as number of linearly independent eigenvectors corresponding to lambda equals 2. This is nothing but the dimension of kernel of A minus 2i. That is the nullity of the matrix A minus 2i. First of all, let us find the matrix A minus 2i, which is 0 to 1, 0 0 minus 1, 0 0 3. Since this matrix has rank 2, if you just look at the matrix, the first column is a 0 matrix, only it has two linearly independent columns, hence the rank is 2. Since the rank is 2, the nullity of the matrix A minus 2i is 1. Okay. So the geometric multiplicity of lambda equals 2 is 1, which is not same as that of the algebraic multiplicity of lambda equals 2, which is 2. Since the geometric multiplicity and algebraic multiplicity of this thing is different, it cannot be diagonalizable. A is not diagonalizable. If the algebraic multiplicity of some eigenvector is same as that of the geometric multiplicity, if this is true for all the eigenvalues, then the matrix is diagonalizable. This is one of the definition of diagonalizability. If it is not diagonalizable, then this option is ruled out. So the minimal polynomial of this matrix is x minus 2 whole square multiplied with x minus 3. So answering option 2, which is wrong, is not diagonalizable. And answering option 4, minimal polynomial and the characteristic polynomial are same. Yes, true. Okay. Now we have the minimal polynomial in which x minus 2 whole square is there. So A is similar to a Jordan block in which one 2 by 2 block has to be there for this 2. Yes, this is there. Okay. And then we must have another block for this 3 of order 1. 3. The rest can be filled with 0. If you just closely observe the matrix B, yes, this is the matrix B. Therefore, A, sorry, the matrix A has the Jordan block which is equal to B. That is the option C. I mean option 3. B is the Jordan canonical form of A. If these things are happening to be true, that is, if B is the Jordan canonical form of A, then of course A and B are similar. Okay, no, like no irrational values or complex values is involved, hence it is similar over the field of rational numbers. That's it. Thank you. We will meet in the next video.